We're now going to take a look at an interesting idea highlighted here by example number 3. What would happen if the surface that I was attempting to work with in my surface integral was actually one that was given by a function? One thing that you'll notice is that if I look at any of the previous examples, I was never actually working with a function. I never had something that was z equals. I never had a surface that could have passed a vertical line test. Right? Both of these were given by some other sort of function that was not a z equals stuff with x and y. So what would happen if I had a function like that as my surface? Could I actually find a way to compute what this surface integral would be? Well, let's go ahead and actually take a look. You might recall that just like we had done in the previous examples, the first thing that I would need to do in this case is to parameterize my surface. So I'll state here that we will parameterize my z equals g of xy as an r of uv. And this is so incredibly simple to do. Note that if I just let x be equivalent to u, if I let v be equivalent to y, then all I would have to do to get a formula for z is to replace all of the x's and all of the y's with corresponding u's and v's in the original given formula. So this could represent a parameterization. And now what I could actually go ahead and do here is to say that I could go and find my partial derivatives. Okay? So this would mean that if I wanted to, I could calculate my r partialed with respect to u crossed with my r partialed with respect to v in the following way. Partials with respect to u would be 1, 0, and then I guess a partial of g with respect to u. And I'll just write it as like this. When I do my partials with respect to v, I would get g partialed with respect to v for that final component. I'll go here, throw in my i's, j's, and k's, and finish off the cross product calculation. For my first component here, I'm going to end up with a negative partial of g with respect to u. And then for my middle component, it looks like here I'm going to get a g partialed with respect to v minus 0. But remember that middle component always gets multiplied by an extra negative. And then my final component here is a 1. This would mean that the norm of this particular cross product should be equal to a square root of my partial of u squared plus my partial with respect to v squared plus 1. And this allows me to go ahead and rewrite my given integral. So my double integral over sigma of my original function can actually be re-expressed as a double integral where I have my function being updated in terms of my parameterization and then multiplied by my norm of my cross product, and then I'm just integrating over some region D down in the UV plane. But there's one other thing here that actually becomes really significant to take a look at, and it has to do with the original parameterization. Keep in mind up here that x and u were actually the exact same thing. Y and v were also the exact same thing. And so when I go ahead and actually take a look at what this means, I can actually re-express this integral up here one more time because I don't have to write it in terms of u's and v's. I could rewrite it back in terms of x's and y's. For example, this partial of g with respect to u should be exactly the same thing as the partial of g with respect to x. Similarly for the partial of g with respect to v. That's the equivalent to the partial of g with respect to y. It's also then the case that if I'm going to rewrite everything in terms of x's and y's, I don't actually have to change much in my original function. The only thing that I would have to change is just the formula that I use for z. I can't put z in, but I could still put in what z is equivalent to. And notice here, z is just equivalent to g of x comma y. And so when I look at these two integrals, this is an integral that is in terms of u and v, whereas this is an integral in terms of x's and y's. The nice part about this is that if I think about the implication here, I already possessed all of the information necessary in the original stated question to set up this final integral, meaning that if I was dealing with a specific function, z equals stuff with x and y, to compute my double integral, I could completely skip creating a parameterization. I already know it will always come out just like this. Okay. I want to go ahead then and take a look at what this means for the following formula, and also to make some kind of more general statements about the way that we can frame our thinking throughout the rest of this section. So note here again, what we had just shown above is that if sigma was a smooth surface and I had a function, I had a landscape, z equals g of xy, and there was some range down in the xy plane that I was going to work over, then two things could be established. First off, we could say that a normal vector to my surface is automatically going to be given by what I have right here. This is something that we established back in section 4.4, and it's then also going to be the case that I could simply rewrite this surface integral using the following formula. Okay, well, if I have this, then there are some other really nice things that I could begin to say. Okay? I want to go ahead and take a look at this. What I could start to actually do is to see when I might actually need to parameterize and when I might not. So I could write something out like the following. So when I have functions, that is, if I have things in the form z is equal to some, I guess I'll say g of xy, so it's like what I have in the box above. That is, if I have a landscape, right, that is going to pass vertical line test for me, then it's possible to compute my surface area like I had actually shown up above. And I can completely skip my parameterization. So I'll just put here C above, right? Essentially, again, the bonus here is that I can skip finding this R of uv. However, if I have a non-function, something maybe like the sphere that we looked at in one of our previous examples, this certainly does not pass a vertical line test. And so in that instance, I have to go ahead and compute this using my parameterization, meaning that I actually had to go through the work to convert my function and to find this norm of a cross product. So in this case, we need R of uv. Okay. There's one other thing to kind of note here, is that functions technically could do a parameterization if we wanted to. Just like we saw up above in this little derivation, there's nothing to stop me from doing a parameterization if I have a nice function. But what's really important here is that R of uv is not necessary. And maybe that means I should go ahead and actually write it kind of like this. I can say that I can skip. I don't have to, but I'm able to, and instead use the formula that I have up above. This can actually save a lot of time, as sometimes finding parameterizations can be difficult, or as we saw in the sphere problem, sometimes the calculation of the partials and the norm of the cross product can be incredibly complex. This is super crucial to keep in mind. There's only one other thing here that technically we should be able to make note of here. Sometimes it's possible, or it is actually possible to derive similar formulas to the one up above if I instead had a y equals stuff with x and z, or an x equals stuff with y and z formula. I'll leave it up to you to figure out if you can determine what the formula would be in that case, but it should be very similar, and really all you'd have to do if you're not 100% sure of how that would work is attempt to rederive it like we did up here. As we move into the next couple examples, we'll start to see that we'll constantly be coming back to thinking about things as being functions or non-functions to help us determine which approach we may want to take when trying to actually set up a surface integral.